Hi, am I audible? So we'll start at around 6 to 6:03. Let's wait how many else joins. Yes, okay, let's start. So hello everyone, my name is Rajat Mukherjee and this is the NPTEL live session for NPTEL course on, yeah, hello everyone, my name is Rajat Mukherjee and this is the live session for NPTEL course on operating system fundamentals. I'm a research scholar at the Department of Computer Science Engineering, IIT Kharagpur. So we will be solving some problems as well as a recap of what was done this week. So let's start the session. This is for week 6. Yeah, so last week we started. So last week we started mm, the last week we started this like CPU scheduling algorithms, and we are looking into various scheduling algorithms. So uh, last week we have gone through two scheduling algorithms. One is first come first serve, another is shortest job first. So let's uh, let's look at it again. So for scheduling means basically processes using CPUs. So we are introduced to two different types of scheduling last week. One was first come first serve, another was shortest job first. So in first come first serve, what was happening? If three processes, let's say P1, P2, and P3, arrives at zeroth time, say second unit of time, and fourth unit of time, so the one that arrives first will be completed first, then the one that arrived second will be completed first second, and then the one that arrived last will be completed last. This was the first come first serve algorithm. Another thing was there, shortest job first. So in shortest job first, what is it? So suppose P1 has a time CPU burst of 4 seconds. P2 has 3 and P3 has 1. So after, and they arrives at respectively this time frame, so a first P1 will be scheduled, then after that which one is the shortest job? P3 is the shortest job, so the P3 will be scheduled, and then P2 will be scheduled. So this is how the CPU scheduling works in case of shortest job first algorithm. Now we are also introduced to two terms called uh, preemptive and non-preemptive. So in preemptive scheduling, what happens? Uh, every process have a time frame. Process has a time frame during with which it can it can utilize the CPU. With which only it can utilize the CPU. So let's say like here in this case, the shortest job first algorithm, thus this intangible is actually, let's say, 2 seconds. So what would happen? So
First 2 seconds.
yeah, yeah. So first 2 seconds will be P1 0 to 2. Then what it will happen? It will take the which one is the shortest job next. So shortest job first. So in that case, P2 will be. Let's assume that it is first come like. Uh, at that case, only 2 seconds are remaining. P2 has P1 has 2 seconds remaining. P2 has 3 seconds, and P3 has 1 second. So it will complete P3 first because there is the shortest job. That is the shortest job. So after 3 seconds, when P1 is done, P1 has two, P3 is done. P1 has 2 seconds remaining. P2 has 3 seconds remaining. So at that time, P1 will be used 5, and then at the end, P2 will be used. So so that is how your preemptive scheduling occurs. That means after every 2 seconds there is a context switch to get in a new process. So that is your preemptive scheduling. Non-preemptive is very simple. Your your first come first serve is a non-preemptive, and like this, which way give the example of only shortest job first. That is also non-preemptive scheduling. Yeah, Sneha.
But in the shortest job first example, you have written P1 will execute. But P1 is of 4 seconds. Huh?
Yeah, so no,
We
no,
should
no.
have.
So shortest of first, I have given the time also, right? So it arrives at 0, it arrives at 2, and it arrives at 3. So at 0th position, only P1 is present. So P1 will be executed. So in the second case, when after 4 seconds, when P1 has completed, at that time it has two options, P2 and P3. So in that case, P3 is the shortest job. So P3 will be completed. After that, P2 will be completed. So this is how our the scheduling algorithms which we are introduced to last week were done. This first come first serve, shortest job first, your preemptive and non-preemptive. Now let's get back to yes, Neha.
Sorry, sir. One more doubt. In the last example where you have used the preemptive condition also,
Uh-huh.
there are you not taking in account of that arrival time? Because like when P1 is executed for two time quanta, P3 is not already present there, right? Because P3 comes at 4.
Yeah. So I said that it has a CPU burst of 2. So let's say the CPU burst is 2. CPU burst is basically uh, the time it is allowed in the CPU. So I said it is 2. So first initially P1 executes. That is
But
what.
by t equals to 2, P3 is not yet arrived. That is what I'm asking.
Oh,
And
okay,
even
okay,
the
okay, okay,
arrival
okay.
time
Okay,
is
sorry. So I just
we
did.
just take
Yeah, I just let me
took
do
the
it again.
time.
Yeah, let me do it again. Okay. Uh, at 0th second you have P1, then P2 at 0th second and 4th. So initially you have P1 for 2 seconds because it is a preemptive scheduling and you have a 2 seconds CPU burst. So when 2 is completed, so then you have P1 is equals to 2
2
remaining,
seconds.
P2 is equals to 3 remaining, and P3 equals to 1 remaining. So again P1 will be scheduled for 2 seconds. So again P1 will be scheduled for 2 seconds, 4. So when 4 comes at that time, P3 is present, uh, P3 is present and
P3.
P2 is present. So P3 is executed for 1 second, 5, and then
P2.
P3 and P2 and P2. So, like in this case, both are similar, but we will look into other examples where these are not similar. Yes, if suppose the CPU burst in this case was like something like 7, and this time frame was 2, then this will be a different impact. Okay, so any more doubt regarding these scheduling algorithms?
No.
Anyone else? Okay, so this was an example of your shortest job first, we this average waiting time calculation. So what is average waiting time? So average waiting time is the time the process waits outside of its schedule. So if you see here, P1, P2, P3, and P4 arrives at 0, 2, 4, and 5 seconds, and each have a burst time of 6, 8, 7, and 3. So in shortest job first, at 0 second, which one is present? This chart is wrong.
P4 is present. It is correct.
How P4 is present?
Arrival time they have not taken into account. They have just taken
Yeah, so that is what I'm saying. That is wrong, right? So arrival time should be taken into account. Otherwise, it will all be.
because the arrival time that you took na in the previous screenshot, like that was not taken ever in lectures. That is.
Oh, okay. Okay, so if we consider this chart only, let's not focus here. So you have been given uh, P1 is you have been given P1 is P1 0th second and bus time of bus time of 6, 8, 7, and 3. 6, 8, 7, 3. P1, P2, P3, P4, 6, 7, 8, 3, 0, 2, 4, 5. 0.0, 2.0, 4.0, 5.0. Yeah, so we have your shortest job first. So at 0 second you have only P1 available. So P1 will be done. After that, uh, P1 is completed at 6 seconds. So what is present at which one is the shortest job? When when at 6 second, the shortest job has to be criteria has to be between P2, P3, and P4. So P4 is the shortest job because it requires 3. So P4 will be chosen. 9 at 9 second the condition is between these two, P2 and P3. In that case P2 will be chosen. that is 16, and after that P3 will be chosen after 24. So that is your shortest job first. So next is the determining the length of the CPU burst. So we can only estimate or predict in most cases. Uh, like it is not easy to predict how much time CPU burst is will be there. So peak processes with shortest predicted time. So you understand, right? So you know don't know how much this burst time will be, right? So you have got a process and a new function. So how are you going to do it? So it is not some hard and fast rule that has been coded in your CPU or your operating system that this process will take this time. It can take more time, it can take less time, right? So it is there is no hard and fast rule. So at the best the operating system can do is do some kind of prediction that this will be the burst time. So these are the criteria or prediction time of the how to calculate the this bus time, CPU bus time. So there are these are some equations, like you can just go through the slides and you can understand that what they are trying to do is basically predict what can be the CPU bus time, and these are the prediction time and all for that is done to predict it. Next, another type of scheduling is there, that is shortest remaining time first. So next one is shortest remaining time first. So in this case, what happens? Uh, so this is basically the preemptive version of shortest job first. So so basically, let's come back to this example. Uh, so you have been given these four processes. P1, P2, P3, P4, and this is for shortest job first. Now next is shortest remaining time first. So this is basically a preemptive version of shortest job first. So what happens in this case? So let's say uh, that each have a uh, like the scheduling happens only when the scheduling takes place once a new process arrives. So scheduler, let's consider this criteria. Scheduler schedules when a new process arrives or a process is completed. So initially there is only one process. So P1 happens. Now after 2 seconds P2 arrives. So 0 to 2 P1 is have got uninterrupted CPU. So what we observe is P1 have after 2 seconds 4 seconds remaining, and P2 have 7 seconds it require. So what is the shortest remaining time? Who has the shortest remaining time? P1 has the shortest remaining time. So P1 P1 will occur for the next 2 seconds, that is up to 4. At that case P1 will become 2 and P2 remains 7. At that case what happened? P3 arrives. So P3 P3 has 8. So next for after 1 second, that is after 5 seconds, what P4 arrives. So P4 has 3 seconds. Now P1 has only 1 second remaining. So between P1, P2, P3 and P4, P1 is still the shortest. So P1 it's over. So after 6 seconds, so P1 is done and dusted. Now you have P3 P4 and P2. So next what happens? P2 is considered from 6 to,
P4 is considered, right?
yeah, sorry,
Once.
P4. I'm talking about this P4 only. P4 is considered from 6 to 9. So after that, what is the shortest remaining time available? P2.
6 to 8 now.
So no, P3.
Time quanta is taken.
So no, 6. P1 is over, right? 6. So from 6 to 9, it will be P3. P4, sorry. So 6 to 9.
6 to 8. Why
Why?
6 to 8 now? Because you have taken preemptive. Preemptive has a time
No.
quanta, right?
So no. So I have taken this condition here, right? The scheduler schedules when a new process arrives or when a process is completed. So what happens? So in this case, in 2 seconds, what happens? P2 arrives. So at that time, I was considering between P1 and P2, which one has the shortest remaining time. Again, at 4 seconds, what happens? P3 arrives. So that time I was comparing between P2, P3, and the remaining time of P1. In at that time, again also, P1 is the highest. So after that, at t equals to 5, P4 arrives. So P4 has 3, P1 at that time has 1 remaining, P2 has 7, and P3 has 8. So again, P1 is completed because it has 1 remaining. So after that, what remains is P4 7 seconds, P3 8 seconds, and P2 7 seconds. So we considered P4 next, 6 to 9, then P2 up to 16, and then P3 up to 24. So that is how here in this case the preemptive schedule happens. Yeah, so again you will say that what is the difference? Almost same, but we will again look at some examples where these two will give different results. That is your shortest remaining time algorithm. So okay, so let's consider this example only once. Okay. Uh, P1, P2, P3, and P4. Yeah. I will share 1 minute. 0, 1, 2, 3 time, and when it burst time is 8495. 495. Yeah, okay. So let's consider uh, shortest remaining time again here. So initially you have only P1 at t equals to 0, only you have P1. So P1 gets here. Now we will consider the same condition again, that schedule when new process arrive or process is completed. So first P1 will be scheduled for 0 to 1, then P2 arrives. So P1 has P1 has 6 seconds remaining after this, 7 seconds remaining after this. Previously it was 8, now 1 second has gone, that is 7 seconds remaining. P2 has 4 seconds remaining. So and then P3 and P4. Okay. So after 1 second, so P2 will be executed from 0 to 2. At 2 seconds, P3 arrives. So P3 has a burst time of 9. Obviously, P2 has 3 remaining, so P2 has still the preference. So again, P2 happens from 2 to 3. Now here P4 arrives. P4 has bath time of 5, and at this time P2 has used 2 seconds and only 2 seconds remaining. So which one has the shortest remaining time out of this? That is P2. So P2 will be completed up to 5, done. Then which one has the remaining? P4. P4 up to 9, done. Then P1 up to 16, done. And then P3 up to 25, done. Is it correct or I did miss something?
P4 10 तक रहेगा मतलब 5 to 9 है should 5
Oh
to
yeah,
10
that's what I'm thinking. Yeah, sorry. Yeah. So this is your shortest remaining time algorithm in this case. Okay. So that is your shortest remaining time algorithm. Mm, so what it would have been if it was shortest job first, like that the non-preemptive function? What would have been the shortest job first? The non-preemptive version. So at P1 will occur from 0 to 8. After that, which one is the shortest job? After P2, P3, P4, then P2 will be executed, then P4 will be executed, then P1 will be P3 will be executed. So this would have been the order. So there is no context switch. So this jump from P1 to P2 and P2 to P4, P4 to P1 and P3 to P1 to P3 are basically context switch. Okay, so this is your difference between SJF and SRT. So any doubt regarding this? Okay, let's come back to scheduling. So next is round robin. So in round robin, the CPU can be acquired only for a time being. That is, let's say quantum queue. Let's say a quantum queue. That is the only time it is available. So be it any process, it cannot take more than 2 seconds or let's say 10 seconds. So that is another way round robin. So what happens in round robin? Let me again draw. Visually, these are very easy to explain. So in round robin, suppose P1, P2, P3 and P4 all arrived at 0th second, and this has suppose 7, 8, 4 and 9 CPU burst time. Then what will happen is, and suppose you have a time quanta of 2, so that means the CPU for each process can acquire the CPU. Process can acquire the CPU for 2 seconds. So what will happen in this case is P1 will be from 0 to 2, then it will pick up P2 for 2 seconds, 4, then it will pick up P3 for 2 seconds, that is 6, then it will pick up P4 for 2 seconds, that is 8. So after one round it will have 5, 6, 2 and 7 seconds remaining. Then again this process will continue. So the thing is, what happens in this round robin or process, you have a natural progression of your flow of your processes. So if you have looked in previously, like in this ones, you see one happens, then it's a P1 happens, then P2 happens, then P4 happens, then after a long time P1 happens, and then after a long time P3 happens. So each process has to wait a long amount of time to get completed. In this case, what happens? Yes, it is taken long amount of time, but there is serial update of movement of processes in the pipeline. So after P1, P2, P3 happens, then again P1, P2, P3, P4 will happen, and so on. That is how it continues. Okay. Yeah, Sneha.
Yeah, like is it necessary that in round robin, uh, even though the time quantum is defined, it is actually following first come first serve, right? So
No.
it can
Yeah,
follow.
yeah, yeah, yeah. It can be a first come first serve, but like you can have some priorities also. Like you will come to priority scheduling. In that case, these processes have attached to some priority. So in what happens in this case, that case, the one that has been scheduled first will have the highest priority, and each time uh, they will be try to be scheduled ahead of other.
Can there be like short job first with the round robin quantum,
Yeah,
that
the
kind of concept?
quantum can be associated with any preemptive scheduling. So any preemptive scheduling, this term quantum appears. Be it be round robin or anything, shortest job first, shortest remaining time. This quanta is associated with all of them. This round robin, that's why can take place in any order. So it can be first come first serve, can also have a round robin. This with quantum here, shortest job first can also have it, as well as shortest remaining time can also have it. Okay, so that is your round robin. This is a round robin setup for quantum equals to 4. So you can see the context switch happens how many times. So as we discussed the context switch. So uh, so if you can see, so this is the with quantum 12 there is 0 context switch, quantum 6 there is 1 context switch, and quantum equals to 1 there are 9 context switch. So so if you look in uh, our example, so this is one context switch, this is one context switch, this is one context switch, and this is another context switch. So what happens in round robin, the number of context switch is high. So this can be a little bit problematic, right? So context switching requires a lot of energy, and it may slow down the process, right? So context switch requires storing of data to your like uh, process tables, p table, and u areas, those kind of things. So it will slow down the entire procedure. So that is one problem of round robin or this kind of quantum one. So it is always this like priority is one thing that is always given in such a cases. Uh, these are various the graphs to show the average turnaround time for each process, if the quantum increases or not. So last, like I said, that priority scheduling is basically a priority is associated with each of the process. So CPU is allocated to the process with the highest priority. So each case, the one with the highest priority is associated with it is scheduled first. So this can be both preemptive and non-preemptive. So SJF is a priority scheduling, where priority is the inverse of the predicted next CPU burst time. So in simple words, what is being prioritized in shortest job first? The one which has the shortest time like burst time, right? So that is what in shortest job first happens. So one problem with priority scheduling is starvation. like in shortest job first is basically starvation. So low priority processes may never execute. So basically in shortest job first what will happen, the processes, if a process has, let's say, burst time of 8, and all the other processes that are coming and going are basically have a burst time of, let's say, 2 seconds or 3 seconds or 1 seconds. So the job that is going to take long will not ever enter the enter the CPU. What I mean to say is like this something. So, you have a process P1, which say, let's say, takes 20 seconds, P2 3, P4 2, P5 1, P6 again 3, P4 let's say 1, and P7 and P8 be, let's say, uh, let's say 5. So as you can see, this is a very long process and these are very short processes. So if the algorithm is shortest job first, so these all processes, even though these all arrives at 0 seconds, you see, if some other process is selected, is in like this one has the shortest job, so always the shortest job will be selected first. So what happened in this case, this P1 will have to wait a very long time to get executed. This happens in also in case of shortest remaining time, the preemptive version. So in every case this happens. So this condition where a process is have to wait a long time to get CPU is basically starvation. Okay. The solution is solution of this problem is aging. So basically, as the time progresses, increase the priority of the process. So as the time progresses, this is very clear. So once, let's say, 4 processes have been executed, so in that case P1, which was 20 in our case, we will try to give it the highest priority so that it is the one which is next executed. So this is some schedule of priority scheduling. So let's say all of them arrived at the same time and each process has a priority of, these are the respective priorities and these are the burst time. So which one has the highest priority in this case? This one, P2. P2. So P2 will be executed first, 1, then P5 will be executed, then P1 will be executed, then P3, and then P4. So that is how your priority scheduling works. Each process have not only a burst time but also a corresponding priority. So now there can be a scheduling which combines both priority scheduling and round robin. So as I said, so not only the CPUs will have a burst time but will also have a priority in that case. So if you see, uh, P4 has a priority of 1, mm, and so the system will execute the one with highest priority process with the same priority will be running round robin. So here P4 will be executed first. Now P2 1, then P2 and P3 have the same priority. So in that case what happens, first P2 will go, then P3 will go, then again P2 will go, then again P3 will go, then again P2, then again P3. Because the condition says the process with the same priority will be running round robin, and this is basically round robin. Then after that P1 and P5 will have same priority, so in that case again the round robin will happen, P1 and P5, P1 and P5. Similarly, so in actual Unix program, there is not only one queue for this scheduling purpose. There are multiple queues. So in a Unix system, there are multiple queues. Suppose this one has priority 5, priority 4, priority 3, priority 2, priority 1. This is, suppose, let's say, your scheduler, and here new process arrives. So when a new process arrives, the process is sent to P1, P5. Then uh, again, if a new process arrives, then it will come to P5. So suppose these have a quantum of 2 seconds. So after PQ2, it will happen when this one is executed for 2 seconds. This will be shifted to this queue, P4. So automatically its priority after one run will be incremented. Similarly, after let it could be like this. So this one, the one with the priority, gets 5 shots, 5 continuous shots of using the CPU. That means it, so if it has a quanta of 2, so it can execute for 10 seconds. It can use the CPU. This total uh, has a distribution of let's say, what I mean to say is this: the CPU will be scheduled like this: 5, 4, 3, 2, and 1. That means at a unit time, 1 unit time, it can schedule 5 processes. At 1 unit time, it can schedule 2 processes. At 1 unit time, it can schedule 3 processes. At 1 unit time, it can schedule 4 processes. That's what I'm trying to say. So once from higher level it goes to the lower level, its priority increases. So when the next scheduler schedules this one of the process, the one here will get highest priority. So this is your multi-level queue of scheduling. Any doubt regarding this? No doubt. I mean, this is how your modern modern OS schedules. Okay, it doesn't use a normal one queue. There are multiple levels of queue. So let's say, even it is possible that each one of them have different scheduling procedure. So let's say this implements first come first serve. This implements like shortest job first. This implements shortest remaining time first. This suppose increment RR, or last remaining time first. So there are lots. So these queues can also have different kinds of scheduling algorithms as well. So the crux is, when a CPU when a process enters, it always gets the lowest priority. As and when uh, it has to wait, like number of context switch happens, it gradually moves from one queue to another queue to another queue. At the end of the queue, last queue is the one with the highest priority. There, let's say 10 processes are executed at each seconds. Let's say at Q4, 8 processes are executed in per second. So that's how priority is given to the processes. So this is all about your multi-level queue. Separate queue for each priority that I said. So highest priority can be simple process, interactive process and all. So this one is your multi-level feedback queue, which was saying that it goes from one to another queue, another queue. Then these are examples of multiple queue. That, like I said, that each queue have its own algorithm. Each queue can have its own quantum and scheduling algorithms. Okay, so that's it with scheduling. Any doubt regarding any scheduling problem? We'll be solving some problems like numericals of scheduling after this revision. Like those who are giving gate, these are very, like there would be a one scheduling question every year. That's guaranteed. These are very common topic. This scheduling part. Okay, so let's go to the next part of the revision of this week. So this is the process synchronization. So this week only we have a very small part of the introduction to process synchronization. The main part is next week, but let's still discuss briefly about this. So what do you mean by process synchronization? What do you mean by process synchronization? Why does a process need to synchronize?
Share share data processes.
Yeah, there are lots of things like that. Uh, Shared data, shared memory. Oh, let me count. So suppose you have written a piece of code. So you have written a program like consider it updates your bank account after each transaction. Okay, so transaction can be debit or credit, right? So suppose in your bank account there is 15,000 rupees. Suppose you have gone to an ATM and you are trying to withdraw 2,000 rupees. At the same time, let's say uh, okay, let's say is your joint account. Let's say your mother or father are trying to make some online transaction for some buying something online. So let's say it is 1,000 rupees it costs. Okay, so after the end of this transaction, what should be the balance? The obviously the balance in there at that case should be 1,200, right? 1,500, 15,000 minus 2,000 minus 1,000, right? So it will be around 12,000. Now let's say this process happens concurrently at the same time, right? Let's think like this. So 15,000, your ATM purchase goes 12,000, it becomes 13,000. 15,000 1000, 14,000. Now let's say this takes 1 second, it completes 1 second before this, and it's, let's say it takes 1 second more than this. So in that case, the latest value that will be updated will be 14,000, right? So though 14,000. So though the required it should be 12,000, but actually my account is showing 14,000. Right? That is wrong balance, right? That should not be the balance. So so when two jobs, that is withdrawing from the ATM as well as buying from your online store, takes place at the same time concurrently, you see there is a problem. So either it can show 13,000 or 14,000, or it can show 12,000. But 12,000 is not always guaranteed. It can show any of these three values. So let's say this is task 1 and this is task 2. So if task 1, task 2 and task 1 is completed first and this task 2 is completed second, then 1400 will be shown, or if the vice versa will be 13,000. So you understand what is the problem of this transaction. Basically the data is not synchronized between both the tasks. So both the tasks, the data they consider as 15,000, but that is not the correct one, right? Correct one, that will not give you the correct answer. So that will give either you a value of 13,000 or 14,000. So that is what synchronization required. So you need to synchronize between the two tasks. So the bank may have to say, okay, wait for a few seconds, another transaction is taking place, let's complete that transaction first, and then we'll come back to your transaction. That is how your bank updates the value. So in simple terms, what does the bank do in this case is basically when two jobs at the same time happens, T1 and T2, so it lets only T1 access the bank account. So what it does, 15,000 minus 2,000, 13,000. So after T1 is finished, only then T2 will start. Minus 1,000, 12,000. So that is how process synchronization happens. So this balance in simple operating term is called critical section. This is called your critical section. So as seen in this example, so only one task at a time can enter the critical section. So either T1, in this case the ATM one, or T2, in that case the online shopping one, only one can enter the critical section at a time. That is your that is how it synchronizes this process. So let's come back to the slides. So any doubt regarding this concept of why synchronization is required? That should be clear. Why synchronization is required. So the objective is basically to introduce the critical section problem, to present both software and hardware solution for the critical section problem, to examine several classical process synchronization problems, to explore several tools that are used to process synchronization problems. So the synchronization term is basically concurrent access to the shared data that may result in inconsistency. So here this is your critical section. So if this data may result in inconsistency, so either the output could be 13,000 or 14,000. So that is the inconsistency we are talking about. Maintaining the data consistency requires mechanism to ensure the orderly execution of cooperating processes. The synchronization mechanism is usually provided by both hardware and software operating system. So let's consider the basic problem of synchronization. So in synchronization, like if you open a textbook like Stalling or Galvin, you will find this famous problem called producer consumer problem. So there are many other problems also, but these like reader writer problem, then dining philosopher problem, there are many are there, but this one is the most common one that is considered for operating system. So you have a pool of data. Job of producer is to produce more and fill the buffer. So job of the producer is to fill this buffer, and job of consumer is to consume data from the buffer. Okay, that is your main objective in this producer consumer problem. Now there are many versions of this problem, that there are more than one producer, in producer one consumer, in consumer one producer, in producer in consumer. So these are many versions are there of this problem. So let's dive into this problem in more detail. So once you have your uh, the solution is basically you can have let's dive in the program first. So this is your basically a producer process. So the job of this process is basically filling the counter. So you have this program while true, while counter is equals to buffer size. Buffer in is basically the next produced item that is inserted into this buffer, and the counter is then updated. So so uh, so if you deep dive into the program, what does this statement mean? While counter is equals to buffer size. What does this mean? This basically means this part of the program checks that whether the buffer is full or not, right? And this part of the then it inserts this into the buffer and then increments the counter. And this is the consumer. So if counter equals to 0, then it doesn't consume. So that means this is underflow. That means the buffer is empty. So let's wait up till then. So when this becomes 1, this part is executed. So that is the buffer item is consumed, and the counter is being reduced. So uh, so so which part of the program do you think is the critical section, the one that needs to be synchronized? So in this producer and this consumer, in both, which is the common part in both of these? Let.
Buffer n equals to next produced.
Uh-huh.
Buffer n equals to next produced. The buffer in arrays.
Oh, okay, okay, no, 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 no. So I don't think that is your critical section. Okay, so the critical section is basically, yes, the buffer is your critical section. The more importantly, your critical section is basically this counter update. Okay, so this counter update is your is the main important part of your critical section. So let me say like this. So you have this buffer. So okay, so this is your buffer, and this is your buffer, and the producer basically inserts into this buffer, and consumer takes item out of this buffer. So let's say for the present, producer has produced up to here, 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 here. Okay, so this is basically a queue. So what will the consumer consume next? The consumer can consume anything, but let's say it wants to consume this first, and the producer will next produce, next add here. Okay, so it needs to maintain the counter, like how much is buffer is filled, or how much it is empty. So if let's say uh, there are more than one producer, so in this case let's say more than one producer, P1 and P2. So in both cases, uh, it's need to maintain where it's the what is the count is currently present in the, up to what this buffer has been filled. So that is maintained basically by this your term counter. This maintains how much is your buffer is full or empty. Okay, so the problem with this counter is, so these if there are two let's say, let only consider the producer part. Let me just draw it again. So for for the time being just consume let's consider the producer part only. So let's say there are one, two, three producers. The task of the producer is to fill this buffer. Okay. Now, uh, what happens when the buffer is when we enter one item, when we enter one item to the buffer, count is incremented by 1. Count is incremented by 1. Right? So if say P1 produces one thing, so count is incremented by 1. So let's say count was basically 1, so count becomes 2. When P2 is incremented, P2 inserts something into the buffer, count is incremented by 1, 3. If P3 is incremented by some is inserting something in the buffer, count is incremented by, let's say, 4. Right? Uh, so there are two parts here. So one is where it is inserting the in the buffer, and what is the uh, current size of the buffer. Okay, so there are one another pointer which checks uh, like where is it inserted. So this is considered as a circular queue. Now, so what happens? So if you look at this code, if you look at this code, this portion, what happens? This in this space, the while counter is equals to buffer size. So basically, we are not updating the value of counter here. We are only reading the value of counter. So you don't need any kind of synchronization or uh, to for this purpose. So counter read can happen anytime. So reading is free. Reading doesn't require like any kind of uh, like synchronization. So that is quite free. But if you look at this part, buffer in is equals to next procedure, in is equals to in plus 1, and counter is equals to 1. Here you are updating the in as well as the counter. So here you need to synchronize where you are inserting the in the buffer, as well as what is the count, the number of places you have inserted into the buffer, number of items you have inserted into the buffer. So that too requires synchronization. Yeah. Yeah, so that is how these here the problem of synchronization takes place. So similarly, the same thing happens for consumer. Consumer also needs to check. So a consumer is not only having competition with the other consumers, it also has the same problem with the producer. So it needs to check whether the what is the size of the currently the um, the buffer to the counterpart, and then it takes out the item that has to be emptied from the buffer. So in that case, this next consume equals to buffer out, out is equals to out plus 1, and counter minus 1 are basically the critical section portion of this consumer code. So the race condition is basically counter equals to counter plus 1, counter equals to counter minus 1. So one way of thinking, you can say that, okay, let's let's use two different registers. So let's rename it and do different registers. But if you consider this example where producer executes register equals to 1, register 1 has a value 5, S1 also executes register 1, because register 1 is the one we are updating during producer, so it updates the value to 6. Then consumer consumes the register 2 equals to counter register 2 minus 1, that is 4. So register 2 and register 1 are simply two different values at the end of the procedure. You see, register 2 has a value 4 and register 1 has a value 6. That is not correct, because uh, in each case the producer has produced 2, so it will both be, this will be 6, this will be 7, and this will be 3, this will back to be 5, right? So the synchronization is again a problem in this case, because you are using two different registers. This one is a little critical. If you have any doubt, you can ask this part. So one solution what they have given is, so we use two different registers, one for implementing this count equals to counter plus 1, another is equal to count is equals to counter minus 1. So initially let the execution interleave with count equals to 5. So initially let's say count is equals to 5. So producer executes register equals to register plus 1, S1 executes, producer executes, register equals to register 1 plus 1. So this one and this one. So the value of register 1 becomes 6. Consumer consumes register 2. So value of register 2 becomes 4. So producer executes this part. This counter equals to register 1. So counter value becomes 6, and then here if it executes this, so counter value becomes 4. So what is the correct counter value? right? This is the thing that is creating the problem. This is quite similar to the banking problem that I gave. So you see, if these statements, let me just draw it. It will be again much easier to solve. So you have two registers. So count is equals to count plus 1, and count is equals to count minus 1. So it uses register R1. R1 equals to count. Count is equals to, sorry, register R1 equals to R1 plus 1. Count is equals to R1. R2 is equals to count. R2 is equals to R2 minus 1. Count is equals to R2. So suppose this one, let's say, is 0, is 1, is 2, C0, C1, C2. So let's say first S1 is, so this let's say happens trying to be executed concurrently. So let's say first S0 and S1 is executed. So if count is equals to 5, so here it will become R1 will be 5. After S1 it will be R1 will be 6, and after S2 count will be 6. Now consider this C0, C1, C2. R1, R2 is 5. R2 count is equals to, sorry, R1 is equals to 6. R2 is equals to 4. Count is equals to R2, that is 4. So at the last step, when you are executing concurrently, what will be the value that has to be the value of count? So if these processes C1 and C is this producer and consumer, like S and C are occurring concurrently, so that means we are adding one value as well as subtracting, after that subtracting one value. So net it will be 0 change. So the value of count should remain 5. But if you look at this, which one of these is the correct value? None of them. So this is the rest condition. This is the one that is causing the problem for your synchronization. This is why synchronization is required. Otherwise, the value of the counter can either be 6 or 4, but not 5. This is the reason you require a synchronization. Now this is clear. After any doubt you can ask. Okay, so let's go for the next one. So that is what I explained in this part, that this part, this counter equals to count plus 1 and counter is equal to counter minus 1, has to be done one at a time. It cannot be done both together. So if it is done both concurrently, the update that is causing a wrong update, either it becomes 6 or 4 but not 5. So that is basically the critical section of the code. So each process takes permission to enter the critical section, it executes the critical section, and once it finishes executing the critical section, it executes the remainder portion of the code. So every process has a critical section. So this update and this update is basically your critical section. So though process P1, this S0, process S0 and C0 are occurring concurrently, only one at a time can update this value. So the process is either S0 first update it, then only C0 can update it, or else C0 updates it, after then only S0 can update it, but not together. If it happens together, this will be the output, either 6 or 4, but not 5. But when you allow only one at a time to update it, so what will happen? First, let's say the S0 occurs, so R1's value becomes 6. Then when 0 occurs, R1's value becomes 6 minus 1, 5. So that is what is the what we call the critical section, the update part in this case. Okay. So entry section, general structure of a process, entry section, exit section. So this is the critical section, and this is the remainder part of the section. So so hardware solution. So there are not only software solution, but there are hardware solution as well. So the task of the entry section will be to disable all the interrupts. When it exists, then only the interrupt occurs. But this must be done in the OS, not in hardware, because uh, these are very impractical to do it in hardware. So there are some issues, like currently running code would execute without preemption in uniprocessor system. Multiprocessor system generally too inefficient, or multiprocessor system operating systems using these are not broadly scalable, so you cannot scale it. So that is the reason hardware solutions are not acceptable. So a software solution is basically like this: turn, we keep a variable turn to indicate which process is in it. So you have turn is equals to j, critical section, turn equals to j, and this. So these j are basically, if turn is equals to j, the p1 is able to enter the critical section, and but only one, this allows only one process to enter in the critical section. The other are in busy waiting state. Uh, so when the turn is j, pi and when the turn is j, and let's say pi wants to enter the critical section, so p1 is at critical section, so it is not allowed. So 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 this you understand, right? So this j indicates that at this time only process j, if it is process j, only then it can enter the critical section. So this is for process I. Okay, so let me again go back to the timer. So you have two processes, P1 and P2. There is your critical section. So so you want the critical section, only P1 can enter the critical section. You want to do something like this. What we'll do? You will use a variable called turn. What you will do, while turn is equals to P2 this. What does this do? So suppose if process P comes here, process P2 comes here, it will go into a while loop. So basically this part of the code will be same in both cases, right? So when P2 tries to enter this, P2 is trying to enter this. So in that case, this condition is true. So as a result, this loop will run infinitely. Now when P1 arrives here, P1 says that turn is equals to 2, but in that case, in his case, turn is equals to 1. So what happened? It will enter the critical section, and it will make sure when it exits the critical section, it makes the turn equals to 2, such that here when the code is turn is equals to 1, and when P2 arrives here, P2 will see that okay, it is turn 2, so let me access the critical section and do it, and in that case turn is equals to 1. Note this part. Yeah. What?
Can you reiterate this part?
Yeah, this is let me say it again. So let's say you have two processes, P1 and P2. So you have a critical section part, right, where only either P1 can enter or P2 can enter. Let's say I want P1 to enter. So what I will the code we will write is like this something, while turn is equals to 2. Turn,
2 denotes P2, right?
yeah, turn 2 denotes P2. So turn is one variable, right? Turn is one variable, and similarly for here P2, we will have something like this, while turn is equals to 1, critical section, turn is equals to turn equals to, we will change the update the value to 1. So what happens in this case for P1? For P1, if the value of turn, if the value of turn is 2, what does that mean? That means currently P2 is executing the critical section. P2 is, if turn equals to 2, that means P2 is currently executing the critical section. So it cannot enter, P1 cannot enter here. But if turn is 1, the value of turn is 1, in that case it can enter the critical section, update whatever the code that is there in the critical section, and then press turn equals to 2. This means okay, P1 has completed. Now this statement means I have done it, P2 please do now. Okay, so it will come here, it will update, so in that case it says turn is equals to 2, so you don't have to wait here, it executes the critical section and then turns the check the turn to 1. So in this case this process critical section execution will always be like this, P1 P2 P1 P2, and
Yeah.
yeah.
Like if the initial condition is such that P1's code is working where it has not entered the critical section yet.
Yeah.
So when P1 is working, then the turn is equal to 1, right?
Yeah,
So how does
no, no,
turn
no, 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 no. Turn can have any value, 1 or 2, anything. Turn is a shared element between both, so it
so
can.
I mean turn turn can be updated in other part of the code also, like to make it get inside that while loop.
Mm-hmm.
That initial condition is not very clear.
Uh, let's say this I say that it is not see this turn is also a this update part is also a part of the critical section, right? So this turn is a shared variable, so this update part is also a part of critical section. Turn as a whole, like when you update the turn, it basically announces that I am coming out of the critical section. So consider turn as a part of your critical section. After it updates it, that means it is the last part of your last line that is executed from before executing the critical section. As a result, there is no synchronization issue, because if you are creating it in the critical section, then there will be no this problem of synchronization. It's clear now, or it out.
Yeah.
Okay, so let's go to the next one. Last one. So, how do you solve the critical section problem? So, so any solution to the critical section problem needs to have these three uh, properties. So these are the properties that any solution to your critical section problem should have. So one is mutual exclusion. So that is, if P1 is executing its critical section, no other process can be executing their critical section. So at one time, only one process can execute the critical section. Progress. If one process is executing, if no process is executing its critical section, then exists some process that wish to critical section, then the selection of the process will enter the critical section. And there is bounded wait, a bound must exist on the number of times a process are allowed to enter the critical section after the process has made a request. So let me simplify this. Again, these are very jumbled words, but so first one is mutual exclusion. Mutual. So what does mutual exclusion mean? Mutual exclusion mean if there are processes P1, P2, P3, let's suppose P1 is using critical section, so only P1 is allowed to use the critical section at the time. P2, P3 cannot enter it. Unless and until P1 completes it, P2, P3 cannot enter the critical section. That is your mutual exclusion. Clear? Next is your progress. Progress means suppose this is your critical section and no process is executing the critical section. Suppose P2, P3, P3 are three processes which wants to execute the critical section, but at the moment none of them are executing the critical section. Then one of the process should be allowed to enter the critical section. So that means progress. That all the processes are not waiting. One is allowed to enter the critical section. That is one other property of any solution to critical exclusion, like critical section problem. And another is bounded wait. Suppose P1 is executing the critical section and another process P2 has stated that I want to use this critical section. So this waiting time between when it has requested for critical section and the time it executes the critical section should be a fixed time. It should not be like that it is waiting, P2 is waiting infinitely to enter the critical section. That is your bounded wait. Clear these 3 points. These 3 points are very important. Like any Viva, anything, people will ask this problem. What are the properties of any solution to the critical section? So any doubt regarding this?
That speed was in the bounded waiting point. What is that speed, relative speed?
Uh, what is the speed relative? 1 minute. So it says that no assumption concerning relative speed of impulse. Yeah, so speed is not the necessary. The necessary is that waiting time. Like it doesn't matter how much time is it, but it says that the waiting, it should not be waiting infinitely. That there should be a way that another process is allowed after some time. So, like what I mean to say is that there should not be that infinite wait for P2 to enter the critical section. There should be a fixed wait time, not that it will eventually like wait for eternity to enter into the critical section. Okay. Okay, so let's that was the end of the recap. Let's jump to some problems. So let's solve these first. These are very good problems I picked. Okay, so you have three processes, P0, P1, P2, with a burst time 2, 4, and 8 units. All processes arrive at the time 0. Consider the longest remaining time first scheduling algorithm. In LFRT, ties are broken by giving priority to the one to the process with lowest process ID. So it says, it means that, so P0, P1, P2 all arrives at 0th. It has 2, 4, and 8 respectively time required. So the question is, what will be the average timer of time? So you will must be asked, like thinking, what is longest remaining time first? I think the name is actually good enough to understand. The one that has the longest remaining time will be executed first. Also, ties are broken by giving priority to the process with lowest process ID. So in this case, P0 has the lowest process ID, so P0 will be executed first. P0 will be executed from 0 to 2.
But that is when there is a tie, right? Tie on the basis of the burst time or the arrival time.
Sorry, I made a mistake. Yeah, so the tie is basically on the uh, remaining time. So in P0, P2, P1, which has the longest remaining time? P2. So P2 will be executed first, 0 to 8. Then P1, longest remaining time, 4, like 12. And then P0. Okay. So what is the average turnaround time? What is turnaround time? So what is the turnaround time for P2? So what is the turnaround time? What do you mean by turnaround time? We discussed it in the last class. So it's basically the average time required required to execute a process, right? So in this case, P2 requires 8 time, P1 requires 12, and P0 requires 14. So it becomes
No, no, please.
how much? 8,
8 plus
12, and
34 by 3.
sorry, I did make mistake, right? 14. So 8 plus 12 plus 14 divided by 3. So that is 30,
34 by 3.
34 by 3. That is basically 13 point something.
No, 11 points.
11 point something, right? So it will be 11 point something. So I guess this one will be the answer, like the closest one. So 11.33. So this will be the correct answer. I didn't check the answers while I picked up. Okay, so do this one next. Try to do this one. What will be the answer? Try to do. So you have uh, processes
3.
three. So
No,
let,
2, 2.
let us do it. So there are three processes: P1 10, P2 20, and P3 30. So now they arrive at 0, 2, and 6. So we are applying shortest remaining time scheduling algorithm. So first P1 arrives. So P1 P1 arrives. P1 has 10 seconds remaining. So P1 gets executed for 2 seconds. P1, then P1 0 to 2. Then P2 arrives. In that case also uh, P1 will be there up to 6. That will be uh, 6. So P1 becomes 8. Here becomes 4. Then P1 happens 10. Then P2
Yeah, P2 happens to 20.
and then
30.
3. Yeah. So how many context switches? 2, right? So the correct answer is 2. Yeah. So one change to this question. So this one which we solved. Let's consider it is preemptive. This part I missed when I took the question. So you have P0, P1 and P2. You are doing longest remaining time fast scheduling algorithm. Priorities are broken with the process with the lowest priority. So mm, burst time of 2, 4 and 8. Okay. So so this will happen like this. Okay. So let's try the preemptive version. So which one will go first? P2, right?
No, but it is arrival time based, right?
No, arrival time are all same. Arrival time are all same. Uh, so all processes arrive at time 0. So we have longest remaining time first. So which one has the longest remaining time? P2. P2 will be executing for 0 to 4. Okay. Uh, then you have the tie of P1 0 to 4, so it becomes 4. So then you have the tie of P1 and P2, right? So which one will be executed then? P1 will be executed, right? P1 will be executed till P1 will be executed till not 8. P1 will be executed till 6. In that time it will have tie between P0 and P1. So then P0 will execute it till 8. After that P1, no, again it is wrong, right? 2, 4, 8. So preemption occurs when uh, uh, based on the time remaining. So first, which is the longest process? P2. P2 will be executed from 0 to 4. So it becomes 4. Next, P1 and P2 will have a tie. So P1 will be executed from 4 to 5. It will become 3. Then P2 will be executed 5 to 6. It will become 3. Then it will become P1, it will be 7. Then P2, it will be 8.
when P1 becomes 3, then P naught will get clarity now.
Yeah, now P naught, P0, P0 1, then P1 9, 10, then P1 will be, after executing this will be 1, then P2 1, then P0, P1, P2, 12, sorry, 12, 13 and 14. Right. So how much time P2 have to wait outside? P2 has to wait outside for 1 second. P2 has to wait outside for 1 second, then 2 seconds, 1, like this to this is 1, then this to this is 1, then this to this is 3, then 3. So it will turn out to be 8. Similarly, P2 will be, P1 will be 4 plus 1 plus 2 plus 2. So it will become 9, and P0 will be 8 plus 3, 11. So it will come down to around uh, 9, 11 and 8. So something it will come down to 39. This will be 10. 8, 10 and 11. So that will come down to 39. So that will be around 13. So average turnaround time will be around 13. So you can go and do it again. Like, let me know if there is any doubt regarding this. Like, this is a very complicated process to do it, but this comes. Okay, so let's not waste time and come to this. So let's say you have three processes, P1, P2, P3, and arrival time 0, 1 and 3, time units as 5, 7 and 4. So you need to calculate the completion order of the three processes under FCFS and RR2, where round robin has 2 unit time, like quantum time of 2 unit. Try to do it. So FCFS RR2. So in FCFS, which one will come first? The one which arrives first. So what will be the order? What will be the order? P1, then P2, then P3. Right. Because that is the order in which it arrives. But in round robin 2, what it will be? First P1 for 2 seconds, then P2 for 2 seconds. So P1 becomes 3, P2 becomes 5, P4 becomes 6 after one round. Sorry, control sheet. becomes 2. So 4 and 6. Then what happens? Then again P1 becomes 1, uh, then P2 becomes 3, and then P3. So P3 is the one that is first completed. Now next P1, that is 1 second, so 13. So then P1 and last P2. So that is the order in which this one is completed in round robin. Okay, so let's come to this one. Uh, so you have been given three processes. This is your arrival times and this is your time units. So, so we are trying to do preemptive shortest job first. Preemptive shortest job first. Scheduling is carried out only at arrival or at the completion of the process. So what is the average wait time for the three process? So this part is important when the scheduling comes at arrival or at the completion of the process. So you have P1 which arrives first. P1 goes for 1 second because after that a new process arrives. In that case, which one has the shortest job? So this becomes 8. P2 has the shortest job. So P2 is executed up to 2 seconds. So in that case, P3 comes, P3 has 9. So which one has the shortest job? 3, P2 only. So P2 happens till 5. Then which one is the shortest job? P1 till 13. And then P3 till 22. So what is the average waiting time? P1 waiting time, P1 has to wait for 4 seconds, right? Here, here till here, 4 seconds. P2 has to wait for 0 seconds. And P3 has to wait.
P2 has to wait for 1 second, no?
No, no,
Second
no.
one.
So it is arriving at 1 second only, right? So there is no wait time, it goes directly. It has 4 bus time, so it has 8 remaining, it has 4 remaining. So P2 directly goes, so it doesn't have to wait for a second also. So P3 will be how much? P3 arrives at 2 and it has to wait till 13. So 11. So it arrives here and it has to wait till here. That is 11. So total wait time is 15 divided by 3, 5. So answer is 5. Okay. So let's quickly come here. So you have a OS which has a round robin scheduling procedure. So and Q is equals to 4. So CPU is now assuming the CPU free now. There are 20 processes waiting in the ready queue. 20 processes are waiting. So the maximum amount of time that a process waits from getting into the CPU before getting into the CPU is how much? So the last process that will go there, so it will be like,
19.
so 19 into 4, right? 19 into 4. The last process will be the 19th process into 4. It is 76 nanosecond, microseconds. So a situation where several processes access and manipulate the same data concurrently and the outcome of the execution depends on the particular order in which access takes place is, so basically you have several processes and manipulate the data concurrently and the outcome of the execution depends on the particular order in which takes place. So basically that is the next condition, because that is your how the critical section happens. So the order has to depend on it. So that is your risk condition. The outcome has to depend on the particular order, right? So if T1 is completed first, so as we see in the example of counter, so one was T1 was increasing the counter 6 and T2 was decreasing the counter 4. So either 4 or 6 will be the output. So that depends on which one is completed first. So which of the following is incorrect? Like starvation is when low priority process might never get executed. Aging is the solution. Aging is the solution to starvation, where priority of the process is increased with time. In priority scheduling, the higher the value of integer, higher is the priority of process. So this one is correct. Starvation is when lower priority process might never get executed. True. Aging is the solution. True, because you increase the priority with time. In priority scheduling, the higher the value of integer, like it is false. Lower the value of integer, higher is the priority. So priority equals to 1 means that has higher priority compared to priority is equal to 5. So this one is the incorrect statement. Next, which of the following statements are true? Shortest remaining time fast scheduling algorithm may cause starvation. Uh, Shortest remaining time, shortest SRT may cause starvation. Right, that is true, because you see, we have seen that in the shortest remaining process time, so suppose even if P0 has arrived fast and it has 20 seconds remaining and other process arrives P2, P2, P3 with 3, 2, 4, 3, like this process time. So these always have the shortest time. So this will not get executed. It will just starve. P2, P3 and rest will always get executed fast. So
If we take the arrival time to be 0, then as short as time to
yeah,
be
shortest
start.
remaining time always takes that part, right? That it is a preemptive scheduling. So after
Yeah.
once, so after 1 second, it will become 19, and then the shortest will be 4, 2 or 3, right? So that is the problem. So this one is also true. So round robin is better than FCFS in terms of response time.
Yeah.
So in terms of response time is because in FCFS one has to wait again for so if it has 9, P0 has 9, P1 P0 has 9, P1 has 8, and P2 has 3. So P1 has P2 has to wait until and unless P1 P0 is completed. But here it does a round robin P0, P1, P2 are interleaved. So option D will be the correct answer because this one is also true. Right. Uh, which of the following is correct? If the time quantum is extremely small, round robin can result in large number of context switches. True, right? So if it is, let's say you the processes are time 8, 10, and 7, let's say 7, and the quantum is 1. So after each second there will be a context switch, right? But if say quantum is 4, so there will be much lesser context switch than previously. So this one is true. The average turnaround time of a set of processes does not necessarily improve at time quantum size increases. So if you have looked at the tiered graph, you see there is no such relevant context. So time quanta increases, that turnaround time increases or decreases accordingly. There is no uh, correlation between it. So this one is also true. The average turnaround time can be improved if most processes finish their next CPU burst in a single time quantum. Yeah, so that is also kind of true because so if after few bursts, if one uh, does it one at a time, so then next CPU burst in general, next average turnaround time can be improved if most processes finish their next CPU burst in a single time quantum. So that is kind of the observation. So this one is also true. So the correct option is D. None of the above is incorrect. So next question is mutual exclusion implies if a process is executing its critical section, then all the resources of system must be blocked until it finishes execution. If the process is executing its critical section, then other processes must be executing its critical section. This is false. If a process is executing its critical section, then no other process must be executing their critical section. So this is true. This is false. This is not true. All the resources are not to be must be blocked. All the resources should not be blocked. Only the critical section should be blocked. So which of the following is correct about atomic action? So while execution of atomic action, no other instruction is executed concurrently. This is true. So when you are increasing count plus plus count 1, only one at a time can be done. Otherwise there will be mixed results. Incrementing or decrementing the counter as atomic action can solve the race condition. True. So only one at a time can be is good enough. Ability to execute actions automatically can provide solution to several synchronization problems. True. So the correct answer is D. Okay. So come to the next one. Bounded waiting implies that there exists a bound on the number of times a process is allowed to enter the critical section, right? After a process has made a request to enter this critical section and before the request is granted, before when the process another process is in the critical section, before our process has made a request to the critical. So it is always A. So a CS1 process is executing it, PI is executing it, PJ has made a request. So it will wait a certain amount of time. Mm, After that, it should be allowed to enter it. So in design of a critical section, each process must ask to enter the critical section in dash code. It then executes the critical section. Once it finishes executing the critical section, it enters the dash part of the code. So first it will be the entry section, then it will be the then it will be if then exit, and the process then enter the remainder. So you have your critical section, entry, exit, and the remainder of the code. So this one, if the following is adopted to tackle the critical section process. So if the process is in critical section, no other process is allowed to enter the critical section. True, that is your mutual exclusion. If no process is executing in critical section, then uh, there exists some process that wish to enter the critical section, then the selection of the process that will enter the critical section cannot be postponed indefinitely. What is this? This is what is this called? This is basically progress. And then there is bound exists. So this is also correct. A bound must exist on the number of times the other process are allowed to enter the critical section after the process has made a request to enter its critical section and before the request is granted. This is your bounded wait. So I will say this solution to critical section problem, race condition or critical section problem is a very important. So always remember these three terms. Okay. So that is the end of today's. So we will again meet next week. Thank you for joining.